Okay, so let's continue from last time, where we implemented linear regression in neural network from scratch. So back then we didn't use any of the tools that we introduced using backpropagation and the Autograd in PyTorch. So here we are slowly bringing them into the implementation. Okay, so we import matplotlib and torch, and then we also import the typing. And the reason is this type hints basically help documentation and what our functions are expecting and returning, and also makes the code more maintainable. We generated a synthetic data, and here last time, if you remember, we had some issues with tensor shapes. Here we basically make sure that we are not getting that anymore. Before going into the details of the code, I want to get your attention for this figure from the book, figure 5.3.1. This is just a schematic of a computation graph. And as you see here, we have the values of x, w, all in square. So these are the items that can take value, and we have some operations over them. So if you remember in backpropagation, we start from last loss value and then propagate that backward. And the last points of these backward propagations are those values that we start from, and we apply some operations. So for example, here, the weights, these two weights, and x, which is the input data. And the rest will be based on these values, or the parameters of the neural network and input data, the leaf tensors. So leaf tensors and non-leaf tensors are important concepts that we have to consider during our implementations. Again, leaf tensors are instantiated directly. They are not the result of an operation over some other leaf tensor. And we keep the value of their gradients. So the function backward, the method backward that you will see that basically apply the backpropagation will store the grad values for these tensors, leaf tensors. For the other non-leaf tensors, the grad will be removed, or basically the entire computation graph will be removed for saving memory, essentially, and the gradient for those values are not stored. So for example, when we initiate the weights and biases, for example here, those are the leaf values. But if we apply some other operations on them and maybe introduce new values, the new value will be a non-leaf tensor. So after calling backward, you can basically print the grad attribute of leaf tensors. But for non-leaf tensors, there will be no grad attribute. If we want to update the values of the parameters following the computation of the gradients, for example, we are trying to update the weights. So previous weight minus the learning rate by the gradient of the weight. But notice that this is a leaf node, and we are doing some operations on that. That makes it a non-leaf node. And then after that, all of the issues that we discussed above. The right way to do it is basically we have to tell PyTorch that we want this to be kept as a leaf node. So this is a way for PyTorch to keep the parameters out updates outside of the Autograd, because otherwise memory usage will explode, gradients of gradients, and then runtime errors when we reuse this modified parameters, and some other problems. Okay, so let's quickly summarize these methods. The torsional grad is very common. We disable the Autograd, and then we can update the parameters. Maybe we want to do inference. The tensor data, this is a direct access to the underlying data. The detach is a way of creating new tensors without the grad history. And then basically it will work like a leaf node. So for example, if we want to do some in-place operation that is not introduced new variables, for example, value x, and we do some operation over it, multiply by 2, we introduce y. Now, if I add something to x, now this is an in-place operation. For example, if we compute the loss as the y sum and do the loss backward. So it basically tells us that now a leaf variable that requires grad is being used in an in-place operation. We don't want that. And here, to avoid that, we have to introduce a new x, and then we continue doing this, we are okay. Okay, so it's good to discuss another behavior of auto-diffin in PyTorch. So for example, if we do the backward once and then do it again, right? Do another backward. This basically adds up the gradient for the weights, okay? Which this will give me W grad as my grad that I want. But here, after doing this step, we'll get grad of 1 plus grad of 2. And that means that basically gradients accumulate. So to avoid that, we have to zero the gradient. So with self dot grad, so whenever, if we haven't zero the grad, in that case, the self.w.grad is not none. We have to make sure to zero it. And this is how we are doing it. We check first, and then we zero. And then after that, we can do a fresh backward. Okay. In PyTorch, we have the optimizers that are basically doing this operation for us, updating the W's and doing this gradient descent. So for example, a stochastic gradient descent is an optimizer that we use like this. Here we compute the new gradients, and then here we update the parameters. So in each forward pass, this will compute a computation graph. And here, if we do the forward pass again, this will make the second graph independently. Then if we somehow let's say we have a loss function here, and we compute the loss here, and if I do a backward here, this will compute the backward pass for the first computation graph, and it will free graph 1. So, but graph 2 is still there. So that's how we know PyTorch is handling this memory or managing it. And if we are not careful, let's say we have a loop over different batches, right? In our whatever data loader we have. And here, so we do a forward pass, we get the inferred y pred with the current model parameters, and then we compute the loss. And let's say we want to store this loss, right? This loss. If I don't do this, say we are doing this instead. Then if I do loss backward, each time we append the computation graph in memory, and then we do the backward. So this is not a good practice because of the memory leak that is happening here. So let's just, instead of the computation graph, let's just store the scalar value of loss, which is, after all, our purpose here. Okay, let's write a summary of this common things that can happen and how to handle them. When dealing with non-leaf parameters, we get this error. For in-place operation, like we did, the issue with computation graph storing gradient that is not converging, and one reason can be we are not zeroing the gradient and there's a accumulation of it. We'll go over the example of linear regression. We will show that there are some best practices that we can follow to minimize this type of errors. Okay, so let's go back to that class of linear regression that we were working on. And you can write then let's write the init value. Then let's write the init method. And here, recall that the learning rate is a float. And let's just put like a default value for that. Okay, so let's introduce the weights. Here, I'm gonna just go with the default for now. And you see that we start from random. And notice that here we have require grad as true. And if you remember, I said this is a leaf value, leaf tensor, and accepts a gradient. For example, input data is also leaf tensors, but they don't have gradients and they are constants. But weights and biases are not constants, and we want to tell PyTorch that. Okay, so let's just reduce this value even more. If you remember, we discussed this in parameter initialization. And here we have the biases, and let's just stick with my own shorter. What else? We have the input size as the input size. And then it's good to have some print statement to just show the sizes. Okay, so with that, let's write the first function. So we have the forward method, and the forward method here takes x, returns a tensor, which is simply the operation in this one layer of neural network. Okay, next let's compute the loss, and then let's do our own backward. So here basically we want to simulate or do what PyTorch is doing behind the scenes. So here we have x, y. Okay, so let's just do like what we did last time. We have the gradient of w and gradient of biases. You see that we already have a nice suggestion. We had a 2 over n here, if you remember, but let's put it here. But we have to keep a value of n if we want to do it, and it's not really necessary. So let's just avoid it to make our life easier. So now you see that we have Autograd-like storing of the gradients, but we discussed that it's always a good practice to check if the gradient is already zero or not. If it's not zero, we have to zero it. So let's do it. Okay, and now we make sure that the gradients are zero, and then we can store them. And then after that, let's go for our gradient step. So let's see what we have. X and Y, and then we return a step. Okay, so notice that here we have the forward, and that computes a y hat. And then we compute the loss here, and then we do the manual backward. One thing that I don't like is we do the forward pass twice. So why we should do it? Let's avoid that. Instead, hat here and y hat here. Update the parameters. Okay, so let's do it. So this is that. And then we return the last item. So here the last item is a float. And so maybe I should say that here. I mean, it doesn't hurt to be more accurate. Okay, so yeah, this basically gives us the step of the gradient descent. Okay, so with that, let's do some debugging. And let's see where are the holes in our code. So first, I'm going to make some data. And then we are running the model. Okay, so let's see what we have. We have the regression model. This is our first step. And we do one gradient descent. Okay, so let's see. Okay, so notice that the problem is here, where we are storing the gradient of the bias that we computed. And the assignment that has an issue is we are assigning a scalar to a tensor. Okay, so that's not what we want to do. So let's fix it. Here, this is a scalar because of how we are computing it. And the good thing is we can just tell PyTorch to reshape that to whatever it really wants to. So let's just reshape it to whatever is the shape of the B grad, right? So let's just write that grad and shape. Actually, you know what? We don't want the grad because we just need the shape of B. Okay, so let's try again. Okay, we got an error and warning, and the warning is we are accessing a leaf tensor. We are making it a non-leaf tensor. Again, that's dangerous. Maybe one obvious thing here is we discuss this, right? So we don't want to update the leaf tensor if the self.w.grad, or same for B, is in the gradient mode. So we have to tell PyTorch that. Okay. So with torch no grad, we want to do these updates. Okay, so that's that. We have another one. So what's going on here? There is a leaf tensor that we are touching it. So we are basically doing some operation on a leaf tensor. Let's find that leaf tensor that we are touching it. So we fix this. This is okay. These are some constant. This is leaf tensor that we introduce, and this is a leaf tensor that we introduce, and we do an operation on it. Oh, we don't want to do that. So let's remove this. Let's try again. And we are good. Let's do another step of gradient descent and see if things are not accumulating. I see that we have some. Let's see if last two, that can remove this. No, we are okay. There is no error. We are good. So far, so good. Let's continue. Okay, so now that we have the manual version in place, let's implement a pure Autograd version of this. So we have a linear regression, and we are going to use the auto version of it. And I want to inherit all what Torch NN has to offer. Okay, so usually what we do here, just to use a like a conventional import. We import torch nn as nn just to be more in line with the practice. So we don't need that. Okay, so with that, we have the nn.Module inside that, and notice that Google Colab already did the super init for me. If, for example, we don't have this call and we want to do, for example, a self-linear layer, like here, if I don't have that yet, for example, if I have this commented, and if I run this, this will fail. Basically, you can think of it like we want to build a house on a foundation, and we have to have the foundation first. And super is basically making a foundation, and then we are building up over it using the methods within it. So for now, let's move this for later and keep it simple for now. I mean, even we can move the learning rate outside of this. And the main reason is we want to give this away to the optimizer, not keeping it here. And we want to keep the architecture as independent as possible from those decisions. So with that, I'm gonna even simplify. And one thing else maybe is to, if we want to compare this with the manual version that we wrote up, let's initialize it to be similar to the manual version. So with Torch Autograd, I want to initialize it. So we want to initialize it as a Gaussian. So let's go back, see how we initialize this. Okay, so notice that we removed that scaling, and this may be a bit large for the starter. And like we discussed, we don't want to do an operation on this after we introduce it as a leaf node. So one way to reduce this is to first just introduce this as a constant, and as a constant, and then after that we will set the gradient on for it. So let's do a check again if everything looks okay here. Yep, so let's continue here. Let's add some print statements to basically check the initialization. And okay. Okay, so we initialized the class and we added a linear layer. Now we want to specify how we are doing the forward, right? So here, let's see what we have as a suggestion. We take tensor, we return tensor basically by doing a forward pass. Nice, good. So what else we want? That's it really, but let's extract the parameters to this way. So notice that we don't one step because we delegate all of that to the optimizer later. So here I just want to write a method to get the parameters. We want to make it easily readable. So let's just do some operation on them. So with Torch Autograd, we want to return the weights. Yep, I want weight data flattened to least and bias self linear bias item. Okay, that sounds like a plan. Okay, so with that, we can start training. So we had training of the manual version, very similar from before. Kind of just, maybe I can add it right after this to be closer. So here we are training the manual where we have a verbose, we have several epochs. Like I said, we shuffle the data and then we initialize the loss and the number of batches. And then we make the batches of X and Y. We do a step descent on this batch. And then we add the loss for each epoch. And we control the number of epochs to compute the average loss so far in the epoch. Then we print this out. Then at the end, we have the epoch losses. So basically the average loss of each epoch. Okay. And for the auto version, so instead of doing this data loading ourselves, let's use the utilities in PyTorch. So the first one is we want to use the data loaders in PyTorch. So we have the tensor dataset and DataLoader, which basically DataLoader handles the batching, shuffling, and also parallel data loading, which is very handy for large data sets. What does the tensor dataset do? It helps us to wrap tensors into a dataset for the DataLoader. So without tensor dataset, we have to manually create our own custom dataset class that keeps the X train and Y train synchronized. And that's a lot of work for something that common. And PyTorch has a way to simplify our life. What else we want? We already import the optim here, so we need that too. Like I said, this provides the optimization algorithms like stochastic gradient descent or ADAM or other advanced algorithms. Okay, so let's use them. So here I'm gonna write a train method for our nice mutated model, which is and we can take the rest. So within this function, we will have the optimizers. Okay, so we can take in the learning rates here. Okay, so with that, let's write the function. So when we take in X and Y, we can make the data set using our tensor data set. Then we have the data loader that takes in this tensored data set and the batches that we, the batch sizes that we determined in the train Autograd function. And this way we can prepare for the optimizer. Of course, we need a criterion here. And let's we have the criterion in nn loss, and that's what we want. So notice that in the suggestion, we had the criterion after the optimizer, which is okay because we are going to use it within the training loop, and we haven't yet written the loop. So it can be before or after. Okay, so with that, let's write the training loop. Starting with the epoch classes that we want to start from empty, and for epoch in the range of epochs, and we have the total loss and number of batches, and then now we can use the data loader And for batch, let's keep it similar to what we had in the manual version, and then enumerate. And we are using DataLoader, and by default it put the 0 grad for us, which is nice. Like I said, this can be a common problem, and commenting out this will see we will see the gradient accumulation. Okay, so with that we have the forward here, and doing this forward, the Autograd will track the operation for us. Then we have the last computation, the backward, and then the update of the parameters using the optimizer. So let's update the total loss, the number of batches, and then we have the average loss and epoch losses. And then after that, we can return the epoch losses. We can add some variables for debugging. Example before the training loop. Let's put a verbose here. Okay, so another one here. And okay, so let's write a main function. And in this main function, we make the synthetic data. Let's do it like last time, where we had a true weight and true B. Let's compare the two model. Okay, so we have the models. Loss of average loss of each epoch, and then do the same for the Autograd. So it's torch no grad. We take in the both the weights, flatten that, and also the biases. Let's see. We get this, and then we have this nice method that does it for our auto model. It's also in the final loss. Okay, so let's run this and train Autograd and train manual. Oh, I didn't run this apparently, so let's try again. Okay, so the manual is trained. Okay, oh, there's an error here. We don't have a forward. That's impossible. Let's go back to, oh, okay. We'd never close this here. Okay, so good. Let's go back and run this. Oh, another error. So our linear regression auto class doesn't have a get parameters. I'm pretty sure I wrote that, so there might be some naming issues. Get parameters, of course. Okay, so let's run again. There will be always errors. So okay, so another one. Let's just look for any of these instances. Where is that? You see that he should be very patient, even with me. We have the final losses and weights and biases. So here was 2, that they are all the same. We can also plot the values of this epoch losses. So let me write a plot. Okay, so we'll add a plot function here. I already have that, and just need to align it. And let's try again. So notice that the Autograd minimizes the loss faster, and that's because of the better SGD implementation than what we did. Of course, the initialization is even here It's not exactly the same, but we didn't let Autograd to go smart on the initialization. The final result of W1, W2 and bias is almost the same, and we are happy with that. So that's that.